Okay, today we're going to look at our sort of last topic for this first chapter 10 part of the electricity that we're going to be doing. Today we're going to look at Coulomb's law. And Coulomb was a French physicist and did most of his work in the late 1700s, so we're kind of in the late 1780s, 90s, that sort of range is when he came up with a whole bunch of theories, but his most famous one is Coulomb's law that we now call it. And basically what he did was he investigated the relationship between charges. So if we have two different charges, what's the force between them? And he figured out that the charge, as the charge increases, so does the force. That makes sense. If you have a stronger charge, it should create more electrostatic force. And he also figured out that if you move them apart, the force between them will decrease exponentially. So he did a bunch of experiments and so on, but for all of his work, we've honored him by calling the unit of charge a coulomb. So if we have trying to explain how much charge is on an object, so we could say it has 3 millicoulombs of charge or whatever. And another thing he was sort of famous for is he was one of the key people involved in creating the metric system, which is sort of an interesting side note. How he did his experiment is he used a torsion balance. And if you remember, we actually did the same thing. We talked about it in Physics 20 when Cavendish was trying to figure out how to get the big G number in Newton's gravitation formula. So what Coulomb did was basically the same thing, and in reality he actually did it first. So the Coulomb used the torsion balance to figure out the charge, and then Cavendish sort of looked at that and said, hey, maybe I can use this to figure out gravity. And we're going to see that the two are actually very, very similar formulas, and they're very closely related. So just a quick explanation. So if you look at the picture on here, what Coulomb did was he would charge an object on each end of the sphere. So what he did was, let's suppose he put a positive 2 charge on that one, and then he put the same charge on that one. He didn't know how much the charge was. He couldn't figure out how much it was, but what he did was he would charge a rod, kind of like what we do in class. We rub an ebonite rod with fur or something like that, and then he would touch the metal sphere, and then he would do the same thing on the other side. So he'd get those equally charged, and then what he did is he swung them over to touch 2 fixed spheres that were neutral. And as soon as he did that, so then he would have got all of the charges to balance out. So let me just kind of rewrite this here now. So if we had a charge of 2 on each original ones and we touched them, then basically what he did then in that case is he'd have a charge of positive 1 on all of them. Or it could be negative. It doesn't really matter what whether it was positive or negative charge. Then what happened is as soon as they were equally charged, because they were close together, they would repel each other. So these 2 on the left side would repel each other, and so would these 2. And then what he did was he measured what that force was. So he had a meter at the top of the central rod or string, and just by measuring how much torque was on it, how much force it was twisting, he could then calculate what the force was between those 2 objects. So he got them to separate, right? That was sort of what happened, was by them separating, he created force, and because it's due to electrostatics, we call it Fe. He didn't know how much the charge was, but he could sort of measure the forces. And what he did was he would change the amount of charge by changing the size of the spheres. So he figured out that it didn't matter how much he rubbed the rod, he would only get the same amount of charge, but if he made the sphere bigger, it would then take more electrons or whatever, and it would be a bigger charge. So he changed the size of the spheres, he changed the distance between them, changed all kinds of things, and he would measure the force that it created. So by calculating the distances, the force, all that kind of stuff, he ended up coming up with what we call Coulomb's law. And the formula that's on your formula sheet is Fe equals KQ1 Q2 over R squared, where Fe is our force in newtons, right? That's our electrostatic force. Q is what we call our charges. So those are charges in coulombs. R is our, just like we did with Newton's formula, R is our distance between the charges. And that one we'll do in meters. And our K is typically a constant, just like we had big G for Newton's gravitational formula. K is a constant. Sometimes we'll you'll hear it called Coulomb's constant, but basically we just say K, and the number it actually works out to that Coulomb calculated was 8.99 times 10 to the 9. And the units to cancel everything out properly is newtons meter squared per Coulomb squared. Okay, so that number is on your formula sheet as well. So they'll have K listed with 8.99 to the 9, and the formula will also be listed. What we do notice on the formula sheet, though, is it's typically written with absolute value signs around the FE. And the reason for that is we don't really care. Force is typically a vector, right? So we have positive, negative, left, right, up, down, whatever. But we don't want to worry about it in this case because our direction isn't necessarily going to be indicated by the vectors of the force. It's going to be indicated by what the charges are. So by that I mean if we were to suppose we have a positive charge and another positive charge, we just plug in our values of the charges, and we plug in our K number, we plug in the distance between them, we calculate what the force is, so we would just get our force answer of whatever, and then by looking at the charges we'll know what's going on. So if the question was saying what's the force acting on the charge on the left, so if we were looking for this force, we would calculate it using the formula, and because they're both positives, we know that they're going to repel, so our force then would be to the left, right? It's going to move away from the other charge. So we just deal with absolute values. We don't care whether they're positive, negatives, whatever. Just plug the numbers in to get your answer, and then we use the idea of positive charges attract or repel, or negative 1 plus 1 minus, that type of thing. Okay? Because normally with vectors, if we say plus or minus, that's indicating direction. But now we're dealing with charges, so plus and minus is actually indicating what the charges are. So a little bit different, so we just got to be careful in that case. So let's do a simple example. So example number 1 here at the bottom, it says calculate the force between hair and a comb. So you comb your hair and you create static, so we can actually figure out what the force of electricity is on those objects. So we just plug in our K value, 8.99 to the 9. Charge 1, you can see it says negative 2 coulombs. We don't care if it's positive or negative, so we're just going to put in 2, and it says micro coulombs. Remember, micro is negative 6, so it'll be 2 to the negative 6. It says the piece of hair has 3 coulombs of charge, so that'd be 3 to the negative 6. And our distance is 0.15 meters. So 0.15 squared is our bottom answer. Okay, so plug everything in, and like I said, it's important. Don't worry about the positive or negatives. That's going to be dealt with later. So just solve it as absolute values or just whole numbers. So we plug all this in. We get a force of 2.4 newtons. Okay, so now what we want to do is worry about the direction. So remember, our comb was negatively charged, our hair we said was positively charged, so now it says determine the force of the hair exerts on the comb. So the hair is going to attract the comb, so we're talking about in terms of what's the force on the comb, we would say the comb has 2.4 newtons to the right. Or you could say towards the hair or something like that. Okay, so that'll be the force in the comb. If the question was, what's the force acting on the hair? It would be the same calculation, but in this case, our hair being positive, the comb being negative, the hair is going to get pulled to the left. So it'd be the exact same number, but our direction would be left. Okay, so you get the idea. Just calculate the calculations, use the idea whether they're positive or negative to figure out which direction the force would go to. So a couple quick things. You notice on the last example we used microcoulombs times 10 to the negative 6 instead of just whole numbers. And that is our typical charge. So if you were to measure charge on an object, typically you're going to be in somewhere in that range. You're going to get 10 to the negative 6 or somewhere like close to that. For it to be something like 1 coulomb, we're talking about something that has a massive amount of electricity or electric charge. Things like lightning bolts have things like 1 or 2 coulombs of charge, so huge amounts of power. So most of our questions we're going to be doing are going to be pretty small amounts of charge. And the reason for that is our particles that are making those charges, the electrons and the protons, are pretty small. So on your formula sheet, if you look at an electron on your formula sheet, the charge of an electron is, they write it as negative 1.60 times 10 to the negative 19 coulombs. And a proton, obviously they'll be the exact same, but positive. And a neutron is neutral, so we say it has 0 coulombs. Okay, so because the electrons are so small, at negative 1.6 to the negative 19, we're going to need a lot of electrons in order to come up with a decent amount of charge. So that's why our numbers are going to be pretty small to work with. And 1.6 to negative 19 is an important number because it's the charge of an electron and a proton. We call it the elementary charge, right? That's the smallest we could get, just one electron. So we use the symbol E, so quite often you'll see that. So that's on your formula sheet. They have E equals 1.6 to negative 19. And let's think about what does that mean? So if we were trying to figure out how many electrons are in 1 coulomb of charge, we can actually figure it out by saying 1 coulomb divided by our elementary charge, 1.6 to the negative 19. If we do that together, so we try to figure out how many coulombs, or how many electrons per coulomb. I guess I got that backwards. So 1 coulomb equals 1.6 to the negative 19 coulombs, right? That's 1 electron. So let's write it like that. So 1 electron has 1.6 to the negative 19. So if we divide those, we would actually see then there's actually 6.25 times 10 to the 18 coulombs, or electrons, in 1 coulomb. So I kind of messed that up, but hopefully you understand what I'm trying to get at here. So a lightning bolt strike, for example, has 6.2 times 10 to the 18 electrons being emitted in that bolt. So it's a huge, huge amount. Okay, so 6.25 to the positive 18 electrons per 1 coulomb of charge. So massive amount. Okay, so if you haven't noticed it yet, we see that we actually get two formulas that look almost exactly the same. So what we just did with Coulomb's law was K Q1 Q2 over R squared. And if you remember in Physics 20, Newton's gravitational formula was G M1 M2 over R squared. So if you look at the two formulas, they look almost exactly the same, and they are very closely related, right? In electricity, we're dealing with K, Coulomb's constant. In Newton's, we had big G, the gravitational constant. We had Q1, Q2, which are charges, charge 1 and charge 2. In gravity, we have mass 1 and mass 2, and they both have R squared. So when you look at these formulas, you might think, hey, these are both exactly the same. But there are some pretty important differences. The key difference is G was pretty small. If you remember right off your formula sheet, G was like 6.67 to the negative 11, I think, something like that. And our K number that we just used was 8.99 times 10 to the 9. So K is huge, right? K is a very large number. G is really small. So because of that, and pretty much only that, the rest of it obviously plays a part too, but because the K and the G are so vastly different, our electric force ends up being a lot stronger than gravity. So far out of all the forces we've talked about, electric would be massively bigger than gravity. Okay? If you think about it, well, that doesn't make sense. Like, we saw yesterday when we were doing the experiment that, there wasn't that much force between our static rod and a little chunk of hole punch paper. But what we do see is, you got to think about it, is for us to take that static rod and lift up that little piece of paper, right? We were able to lift it up. We only had a little bit of charge on there, right? We had a little bit of charge by rubbing it, but it was still strong enough to lift that piece of paper up, where we were overcoming gravity, right? We got gravity that's pulling that piece of paper down, and our electric force actually lifted it up. So for that to happen, obviously electric force has to be larger than gravity, right? That electric force has to be bigger, otherwise the piece of paper wouldn't have been attracted to the rod. So just in a simple, small example like that, we overcome all of the gravity force acting on it, and the electric force was still quite a bit stronger. So that's probably one key thing to remember in terms of our forces so far. Electric force is hugely bigger than gravitational force. And another kind of key difference, electric, we can measure whether things attract or repel. The formula will do both, right? Whether it's positive or negative doesn't really matter, where gravity only deals with attraction. What's the force of a Earth pulling somebody down towards it, right? It's only attracting the two objects together. Okay, a couple examples to go through that you're expected to be able to do. So the first one is, we've got three charges in line. So you can see the amounts of charge on each object. And the question's saying, what is the net force acting on the one to the right? So we're trying to figure out what is our electric force on the Q3, the one on the far right. So because there's other charges, we have to take into account all of them. So what we have to do for step 1 is we need to figure out the charge between two of them. So let's do the charge 1 and charge 3. You can see charge 1, I've colored it red to show that it's positive, right? It's positive 1.5, where the other ones are negative. So sometimes colors will help you separate them, or just be careful about the positive negative idea. So in this case, when we put in our numbers, we'd have 8.99 to the 9 for our K. Our charge 1 is 1.5 to the negative 7. Our charge 3 is 3.5 to the negative 4. Okay, remember, don't worry about positive or negatives. And then our distance is, we've got to do the total distance, so we'd have 3.1 meters. And we've got to square that. So when you do all that on your calculation, we get 0.05 newtons. Okay? So now we want to be careful is what direction is that going on. Q1 was positive, Q3 is negative. So that means Q3 is going to get attracted to Q1. So this is 0.05 to the left. Okay? So now what we want to do is the same calculation, but we want to do it for charge 2 and 3. So we'd still have our 8.99 to the 9. Charge 2 this time was 2.3 to the negative 7. Charge 3 is still 3.5 to the negative 4. And now we're dividing by 1.7 squared. So if we do that calculation, we get 0.25 newtons. Now I'll go back to the question again. They're both negatives, so that means they're going to repel. So that means charge 2 is going to push Q3 away. They're going to repel. So this one will go to the right. So now our question is, what's our net charge? Because we're just dealing with left and rights, we just do a simple vector calculation. So we have 0.25 to the right, and we're going to add 0.05 to the left. So think of that as being negative if you want. So our net force then would be 0.20 to the right. Right? It's probably a good idea not to do negatives, positives, just sort of keep your left and right separate if you want in that case. Okay, so that's it. So pretty simple question. Use the formula, figure out what the force is, and then just combine them like you would in terms of vectors. One more example to look at, same sort of setup, except this time our charges aren't in a straight line, they're in 2 dimensions. So we basically have to solve this question just like we did before with momentum vectors or any other kind of vector question. Just make sure you solve it properly and then do your triangles afterwards. So in this case we got 2 coulombs and 1 coulomb at 3 meters. So let's plug those in. So we'd have 8.99 to the 9 times 2 times 1 divided by 3 meters squared. Okay, and for that one we get a massive amount. Like, because we're dealing with 1 and 2 coulombs, we're getting a huge amount. So that one ends up being 1.998 times 10 to the 369, it looks like, what I got on my calculator. Okay, and then we want to do the same thing for the other two, so the red one and the green one in this case. So we'll do that electric force. So 8.99 to the 9, this time 1 and 4. And our distance is 4 meters squared, so we do that one, we get 2.248 times 10 to the 369 again. Okay, so we've got our 2 forces. Now all we got to do is be really careful about our directions. So our first one, they're both positive, so that means Q2, right? That's what we're trying to figure out, is what is our net force on Q2. So these ones are going to get repelled, so Q1's going to push Q2 straight downwards. Q3 is also positive, so it's going to push it over to the right. So you can see in my diagram below, we just have to take our 2 vectors then and combine them as a triangle. So we've got our 1.998 going downwards, so we've got that vector going down. Our green one is pushing it 2.247 to the left. So then all we have to do is draw a new triangle with those 2 vectors and solve it. So if we use Pythagorean theorem, we try to figure out what our net force is. We end up getting 3.0 times 10 to the 9, right? Just 1.998 squared plus 2.248 squared, square root your answer. And then we also need to calculate our angle, just like we normally do for questions. We want to go tan of 2247 divided by the 1997. Second tan that answer, and we get an answer of 48 degrees. So in this case, we would say 48 degrees west of south. And that's our final answer. Okay, so you can see really we're doing nothing different than we did before, just a new formula, a little bit different than Newton's formula, but same sort of idea. And there's a few examples showing you how to work it. And that's all.